Hi everybody. Just from the looks of it, it doesn't look like there's all that many laptops, are there? How many? Raise your hand if you have a laptop. Oh, actually, there's a lot more than I realized. Okay. A lot of you hadn't taken them out. Okay, cool. So, yeah. Welcome. Thank you for coming out. This is a great crowd. I'm glad to see there's so much interest in this. I have a lot to cover, so I'm just going to go straight into it. You're looking at what's called a brainbow. This is a way of imaging actual neurons in the brain. We're going to look at artificial neurons in just a few minutes. I want to start by telling you about how, if you get excited by what we're doing today, there's actually a lot more of this that you can see online. I've been compiling with collaborators a website called ml4a.github.io. It stands for Machine Learning for Artists, and it's basically a bunch of instructional guides and software, and also a book in progress about this topic that I've been kind of using for my workshops for the last couple of years. And so most of this is kind of coming from there. And I've been having lots and lots of workshops. This is probably one of the biggest I've ever had, so they're usually like 20 people. But I think we'll kind of manage now. I'm also currently teaching a class, like a full class at New York University at NYU. And I'm putting all the lectures online, so if anyone is interested in all of this covered in much more detail, this is also a really good place to go. So the idea is to talk about machine learning, to give you a little bit of a feel for the topic more generally, what it's for, and what's so exciting about it, and also what are some of the more creative elements of it, more creative things that you can do with it, applications that are not necessarily just the ones that are kind of for industry and commerce, but actually more expressive and creative. And I think we'll probably kind of get through this stuff. I'll talk about the field really generally, and then give you a very, very quick primer about how neural networks work, because neural networks are the sort of dominant algorithm within the field right now. And then I'm going to show you a bunch of demos that you can try online. I think hopefully with the internet speed here, everyone should be able to participate. And this stuff we'll see. I think in the amount of time that I have, I might just be able to just show these to you, but kind of ask that you do it in your own time. And that's all. So let's kind of get into it. So machine learning. Raise your hand if you feel like you understand in principle what machine learning is. Maybe not what it's for, but okay, not so much. We've had this field of artificial intelligence for a very long time, and machine learning has kind of emerged in the last 30 years or so as an approach to solving tasks in AI. And the approach is to say that instead of hand programming some kind of a function that does what you need it to do, you instead get a whole bunch of examples of the task that you need to have done, data, and then you actually fit a function so that it performs that task very well. And this was actually, even though machine learning as a term has only been around for 30 years, this was actually the original approach to doing AI in the late 1950s when we first kind of came up with the term. And in the late 1950s, the very first neural networks for image classification were developed by the US Navy. Basically, you're looking at it, it's basically like 400 cadmium sulfide photocells, like photoreceptors, that would be used for trying to detect ships, I think. That's about it. This kind of stuff is microscopic now, and it wasn't actually all that good at what it did. Nevertheless, the New York Times, when they found out about it, they wrote that the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So that's the New York Times in 1957. So if you think AI hype is really, really bad now, this is pretty radical, I think, for the 1950s. So because of this kind of coverage, let's say, the 1960s were really like radically utopian, right? So if you look at all of the movies and the cartoons and all of the sort of culture that was being produced, everyone thought that we would have, hyper intelligent robots by the year 1970, and we would be living in a sort of like paradise. But of course, this didn't happen so quickly, and so we went through a period for about 30 years, what was called the AI winter. And this was kind of when everyone lost hope in artificial intelligence. They thought it was kind of like false promises. And all of the sort of culture, like the movies, this is from Blade Runner. Everything was very like dystopian. And what's happened more recently is that AI is starting to make a comeback. And the reason why it's making a comeback is that it's starting to work, actually, for a lot of things that we find interesting. There's been a ton of investment into it. There's been a lot of interest from not just academic circles, but also like commercial, industrial, because now it's actually able to affect some of the things that we all do in sort of everyday life. And so for that reason, we're back in another hype cycle. There's like a lot of excitement and promise. You have the CEO of Google, basically the world's largest tech company, that's saying that AI is more important than electricity and fire. And this was just a few months ago. So we're kind of back in the same territory that we were in the 1960s, I think. So we'll see how far this second bubble takes us. So anyway, there's been a ton of interest, and because of that, there's been a lot more university education, but also like a lot more things like this. The really new thing about machine learning these days is that it's spreading outside of academic circles and into more non-traditional circles. Like most people, I'm sure almost everyone here is not a researcher in AI, right? Because, or maybe some of you are, in which case I don't know what you're doing here. But in any case, like that didn't used to exist at all, because now the field has become a lot more accessible than it used to be. So some of the things that it's beginning to work, like some of the things that we can now do are applications in particular of computer vision have become very, very prominent. So you can think of things like self-driving cars, medical diagnostics. A lot of these algorithms are now able to read things like MRIs and CT scans much more effectively than human doctors can. It's also being used to decode audio into speech, turn speech into audio, or text into audio. And it also has a bunch of cool artistic applications, as we'll kind of get into. As I said before, one of the really great things about the most recent wave is that it's much more open and accessible than it used to be. Even about 10 years ago, if you wanted to study machine learning or anything related to AI, you would have to be a graduate student at a university. You'd have to get a bunch of $200 textbooks. And now it's become a lot easier to kind of do this. Not within these kinds of environments. You can actually, all of the research is open access, typically, being shared predominantly on archive.org. There are a lot of open source frameworks for running machine learning on your own computers. So things like PyTorch and TensorFlow and Keras. There's even whole platforms for for companies to outsource data science tasks that anybody can basically contribute to. So that's Kaggle. And a lot of this stuff is also being freely discussed on social media, so in particular on Twitter and Reddit. There are entire channels devoted to machine learning that you can kind of discuss with people. And so more and more you see that the sort of barrier between the research institutions, or at least the social barrier between research institutions and everyone else, is breaking down. The downside of deep learning is that it requires a lot more computation than it used to be, and that's not easy to get. That could be very expensive. But we'll talk maybe towards the end of today of how you can maybe kind of mitigate that. So I've mentioned this term deep learning a couple of times. So what is this deep learning? So deep learning as a term has been around for the last 5 or 6 years, And it's kind of the strain of machine learning that is most responsible for the recent success. And it mostly refers to a few innovations that have been made over the last, depending on who you ask, like let's say between 10 and 30 years. And the way that, the thing that deep learning has really contributed is that before, the way that machine learning used to work is that if you were interested in, let's say, computer vision, you would have to do a lot of what we might call feature engineering. So taking an image, let's say if you're interested in classifying images, you would have to apply a whole bunch of very domain-specific algorithms to extract statistical features from the image and then plug them into some learning algorithm, and then that would give you the information about it that you want, like a label. And in deep learning, all of this is now inside the learning algorithm. So basically, we have gotten rid of this idea that the representation of the image, after the pixels, let's say, we've gotten rid of the idea that we have to actually figure that out ourselves. We can actually have a neural network do it for us in the process of learning how to do the task. And this has meant that the algorithms have become much bigger, require much more data, require much more computation, but they do everything for us. And so that's kind of the trade-off. They're also much more sort of opaque, or let's say they're hard to kind of see inside, and that has its own sort of implications, and we'll kind of show a few of those in a few slides. There's 3 types of machine learning, roughly speaking. That's kind of an oversimplification, but you'll see that in a lot of textbooks, let's say. Supervised learning means you are trying to learn how to do some X to Y task. So image classification is an X to Y task where X is an image and Y is a label. So you're trying to learn a function that takes some kind of data and maps it to another kind of data that might be more useful to you. Unsupervised learning means you just have data, but there's no labels. There's no function necessarily that you're trying to map. Unsupervised learning is kind of more experimental, you might say, and has less concrete applications. But one really interesting application that's very, very interesting to myself and to people who are, like, let's say, artists and other creative people, is the fact that with unsupervised learning you can fit what are called generative models. And generative models are models of the data that can generate new samples like they look like they came from the original data. And that's quite interesting. And if we have time, we'll see some of that at the end. We're not going to talk at all about reinforcement learning, but it's kind of cool to know about. Reinforcement learning is basically agents interacting with environments. So it's much more dynamic, let's say. So like right now, most reinforcement learning is trying to teach AIs how to play video games, right? Because, that's the cheapest way to do it. But in the future, this is kind of what we might use to create agents that can interact with people in the world, because they have some notion of an external environment that they interact with and they have some effect on, and they have to learn on the fly. So this is kind of much closer to kind of real life. But it's certainly much more experimental, and probably we won't get to it so much. The idea of supervised learning, which I mentioned, which has labels, is that you're trying to fit a function that maps some data X into some other data Y. So that's really, really general. So like a very concrete example of that is taking an image where X is the pixels and finding from it, using this function, a label Y, which refers to what is inside that image. Is it a cat? Is it a dog, right? And the way that F is determined, this function, is determined using a training set of data, like a training data, examples of X and Y that you know from before, and a learning algorithm which can learn the relationship between X and Y. So, we won't talk about this in detail next week because I won't be here. So like one example of this is image classification. So like as I said, determining that this picture is indeed a dog rather than a piano. And another example of this is regression, which is almost the same as classification, except instead of dealing with categories, you have continuous values. So let's say you wanted to predict how much snow is inside this image. You know, can you teach an algorithm to look at a picture and tell you how much snow is on the ground? So that would be regression because the amount of snow is a continuous value. Other applications of machine learning that fit this kind of paradigm of mapping one kind of data into a more useful kind of data is what you call sentiment analysis. So taking text and figuring out the emotion or the sentiment of it. So like, let's say you're reading reviews of restaurants. Can you determine whether they're happy or angry or pleased and so on? Speech to text is another one of these. You take some audio and you figure out the text that is being spoken. So that's your Siri and your Alexa and your Cortana and all of your sort of personal assistant applications. Determining where objects are inside of images. Actually finding objects inside of the images and labeling them. Finding where people are. This image is actually wrong. So there shouldn't be a skeleton on the left side. It's like taking the image on the left, the video on the left, and finding where the people are. Same thing. So kind of mapping out where body positions are inside of an image. Taking images and segmenting them into the actual parts that are inside of them. So here you see that the pillows are labeled yellow, and the TV is or fireplace is labeled red. So this could be useful for, let's say, self-driving cars to be able to tell apart the road from people, pedestrians, other cars, and so on. There's a lot of really interesting applications in trying to recover lost information. So turning black and white images into color images. So for those of you who only have black and white photos of themselves as babies, this might be a good way for you to like actually recover what you looked like back then. And as I said, art applications. So like redrawing the Mona Lisa in the style of Van Gogh. So this is kind of like a cool little toy. Like it's called style transfer. It's an application that you can use to make interesting aesthetics. And de-blurring images. This is one of my favorites to show people because if you've ever seen like a TV show that tries to protect people's identities by blurring them, well, that's broken. So use just like a box, like a gray box. So image to text. So now you can have machine learning algorithms describe in natural language what's inside of an image. So here's some giraffes standing next to each other. So that's pretty cool. And you see a lot of these related algorithms for example, writing newspaper articles. Like in the future, maybe we'll have AIs writing summaries of newspaper articles for us, or executive reports, or this kind of stuff. And then this is also like one of my favorites to show. This is the other way around, right? We have image to text. This is text to image. So you input some text, and then a neural network sort of imagines what it is that you're writing. So this is a woman eating a delicious sandwich. As you can see, here's the woman eating a sandwich. And this looks really, really weird, right? Like, but in a few years, this may start to look, and maybe a lot less than a few years, this may start to look really realistic. And I'll show you actually like some examples that are beginning to reach towards that later in the session. Image to sound. I mean, there's just all sorts of combinations that you can create. I want to kind of keep going here. Speech transcription, speech synthesis, so taking text and creating audio from it. And we've been able to do this for a long time, but using, again, handcrafted algorithms that sort of modeled an entire like vocal modeled vocal cords and then kind of like run this expensive physical simulation to create text or to create audio that's saying something. But now you can just do it from recordings, just using data. And that means well, that means a lot of things, and we'll kind of get to that. There's a whole category of neural networks that operate on sequences of data. They're called recurrent neural networks. So this is kind of used to do things that involve unbounded sequences of data. So for example, language translation, right? I just put this into Google Translate. I don't know if this actually, is that a good translation? Yeah? Okay, so Google Translate, 1 for 1 today. So language translation generally works this way, so sort of like sequence to sequence. Very interestingly, there is some recent research that, so it used to be that the way that you would train a machine learning algorithm to do language translation, it would be to have parallel texts. So like you have one text in one language and another text in the same text in another language, and then the neural network would kind of model the like sequence to sequences, and it would learn it that way. And now it turns out that you don't even need that. So there's like really interesting work where they just take tons and tons of text in every single language that's not at all paired, and then it's really hard to describe how this works. But it actually learns the translation by kind of figuring out the structure of each language individually. Whenever this kind of research comes out, the press usually labels it as like Google's AI learns its own language or something like that. But it turns out it's much less magical than that. But it is nevertheless like quite interesting. Anyway, so a little bit about how neural networks work, because neural networks are kind of the way that most of this stuff is being done right now. So let's do a little exercise. I want you to look at this text over here, and I'm going to give you 1 minute, right, to look at it, and then I'm going to go away from the slide, and you need to write down all of this, right? So you have to memorize it, okay? So 1 minute, okay? Like yeah, pretty difficult, right? Okay, so that was unfair. Let's do a different text. Can you memorize this? Right? So you're looking at this, and it's the same amount of text, right? So it should be just as hard to memorize as the other text. But right away, your brain is like forming some patterns, right? You're able to form a sort of mental representation of this that's simplified. You have this natural capacity to find patterns inside of things, and then to recombine those patterns later into the original thing that you're seeing. And you don't even know how much of this you're doing at all times, right? Because you're just bombarded with information, like sensory information. But your brain is very, very good at like forming representations. And this is actually kind of a little bit how neural networks work as well. They're trying to look at raw data and find patterns. And then by finding patterns, it can reduce the amount of information that it needs to know in order to reconstruct the thing later when it needs it. So features, these are called features, as we sometimes say. Features are like statistical patterns inside of data. And our brains are really good at finding features, and it's basically used to kind of form a representation of data. So neural networks, we don't have nearly enough time to like go into these into very much detail, but I'll just give you a very high-level overview. Neural networks are these data structures that look something like this. They look something like this, except instead of having maybe six of these cells, you might have like 100 million of them, which is a little difficult to fit on my computer screen. So I'm just showing 6. But the idea is that you have on the leftmost side, let's say, an input layer, which is a bunch of neurons that accept some input data, and then the data kind of propagates forward through these connections to other neurons arranged in layers. And it does this sometimes many times. And the reason why it's called deep learning, as you sometimes hear, is that there are many layers of this processing happening now, maybe sometimes dozens or even hundreds of layers. And these connections control how much of that data is being moved from this neuron to this neuron. It's kind of like it's a weight, as we call it, and the weight either like controls how much of that signal we let pass. And this is the reason why they're called neural networks, is that they're a very, 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 very simplified version of how the brain works. The brain also is composed of many neurons, and they're firing basically electric signals to each other through these connections that are called axons or synapses. And then the axons and synapses control how much of that electrical signal goes from one neuron to the next. And well, yeah, and of course, like the amount that it lets pass is kind of something that is to some degree hardwired, and then to some degree is kind of learned mostly in childhood, right? You're kind of training, yeah, when you're training a baby, you're training a neural network in some sense, you know, to figure out what these connections should be. Well, so like, for example, how would we use this for an actual task? So a simple task would be something like image classification. So you have an input image of a number, and you're trying to figure out what number that is, right? And you might have a neural network that has it as at its input layer a series of pixels, and then it propagates forward through one or more layers, and then at the end you have 10 output neurons which correspond to each of the actual numbers, the digits, and then whichever one has the highest signal, you predict it's a 2. Sorry, you predict that class, right? So this is a 0. This is supposed to be 0. This is 1. This is 2. And so this neuron right here had the largest value at the end. And so the program says it predicts that this is a 2. And the way that this is done, the way that now at first it won't do this, right? This is kind of magic, right? Like why is it correct? You know, why is it not making errors every time? And at first it will be making mistakes because we don't know what the weights should be. We have to just make them random. And so if we make the weights random, the behavior of the function will be random as well. But if we train the system, and by training it means figuring out what the weights should be in order to have good accuracy, it will get better and better. And the way that it does this is through a learning algorithm that usually what is used is some variation of what's called gradient descent. And gradient descent is actually like a very, very general mathematical optimization process. And maybe you might be familiar with it. In any case, it took us a really, really long time to figure out how to do this, not just to do this theoretically, but to also do it practically, like efficiently. Because as it turns out, it's really, really hard to do this efficiently because in neural networks that we have, we might have 100 million, like hundreds of millions of these connections. And to optimize hundreds of millions of numbers at the same time, it turns out, surprisingly, to be very difficult. But starting roughly around 10 years ago, we actually began to do that very well. So now in the process of training is iterative. So it's this process where you keep on feeding it more and more data, and as you do, the weights, these connections, change gradually, and as they do, we are forming a representation of the data. Right? So we're forming a representation of these numbers that is able to figure out what the sort of high-level statistical features of them are. Right? And so you see 0, 1, 2, 3. You see the numbers kind of emerging, right? And that's the neural network. These aren't actual numbers. They're just representations of the numbers encoded inside of the weights that are learned automatically through the process of gradient descent. So let me do a quick demo for you of an actual trained CovNet viewer. So this is a demo that you can use. You can download this online. I'll show you the links later. It's on mlfrey.github.io. This is using actually this. How many of you were in Zach's workshop? Some of you. So this is all made in open frameworks. I think he was using open frameworks for that. So this is a neural network that you can run inside of open frameworks. And what it's doing is it's actually visualizing the activity inside of a trained convolutional neural network. I didn't mention what convolutional is. Don't worry about that for now. But basically, you can see that what it's doing is it's pulling out all of these statistical features about me, right? And you can actually view the weights here. If you look at this, these are the weights that we were talking about. You can actually visualize these connections, and then these are the actual like the amount of each of those patterns found inside of the image, right? And so you see that it's finding all of these interesting patterns, right? And I mean, a lot of them are very repetitive, but basically it's finding edges, horizontal edges and vertical edges and diagonal edges and things like that. And what happens is you go through these layers, and what you do is you extract features, and then in the next layer you extract new features from the old features. So if in the first layer we found things like edges, then in the second layer we might find things like corners, because a corner is a combination of a vertical edge and a horizontal edge, let's say. And then in the next time we do this, we might find something even more complex. So instead of a corner, you have maybe a shape, like a rectangle or a triangle or something like that. And then as you keep on doing this, the features that it finds become more and more complex. And so they go from edges to corners to shapes to maybe primitive objects, like a window or a door. And maybe they go to more complex objects like a car. So here, I'll show you an example. Now, it's not written anywhere what these actual features are, but you can actually kind of try to interpret them. So I'm going to show you my favorite neuron here. I use this one all the time. This is Confor 156. So what is that? Right? That is a face detector, right? I'll prove it to you. So I'll like hide. It goes away. Yeah. So that's a face detector, and that's interesting because in the process of training, we never told it to look for faces. It just found faces, because the training process involves learning how to classify lots and lots of different kinds of images, many of which have faces, and many of which have categories of things that have faces, like people, and actually it doesn't have people, it has mostly dogs. This particular network has like 100 breeds of dogs or something like that. It's really, really good at telling apart different dog breeds. So but in any case, like dogs have faces, humans have faces, right? Cats have faces. So it's kind of useful for an image classification system to find faces, because that's information that helps it form a representation and then kind of do the classification much more effectively. So at the end, what happens is we can now do classification. So if I that's horrible. Come on. It's iPod. There we go. See, stupid network, thinks it's an iPod. It's actually an iPhone. Now, seatbelt. Someone mentioned seatbelt. Bow tie, right? Suit, right? It thinks I'm a bow tie. Why would it think I'm a bow tie? Does anyone have a guess? Anyone want to take a guess at why it? Do I really look like a bow tie? Like, am I particularly bow tie looking?
Because of the background, you interpret in the.
That could be, but there's possibly a more like an even more important reason. Well, so the idea is that it's trained on images, and many images are labeled bow tie, but many of the images that are labeled bow tie are of people that have bow ties. And so this is called sampling bias. It's kind of like different objects can bias the label that's associated with bow tie. So bow ties have people, So the first time I looked at this, the first time I used this application, it was like wig. I was like, all right, I need a haircut. Yeah. Huh? What was that? Oh yeah, good idea. Actually, the bottle works pretty well. Yeah. So does microphone, but I don't have a proper microphone. Oxygen water bottle. Barely, but it's got it. Yeah. Sometimes if you turn it the right way, it's So like more images are like the water bottle goes this way, I guess. I don't know. So yeah, that's that. Oh yeah. It's looking for it in real time. So what are some things that you can do with neural networks, like core applications, let's say, that are useful for other applications? So when you form this, like usually we kind of show this, that it's doing some important task like classification. But the thing is that the classification is almost like not the most important aspect of this. The most important aspect of this is everything before the classification, the representation that it learns from the image. When you have this representation, it's like you have this statistical vector that tells you all of the qualities of that image. And you can use that to do interesting computation on top of it. So for example, if you've ever gone to Google and you go to the image search and then you just upload another image, this is like reverse image search. So you put in an image and it finds you more images like that image. So how does it do that? Well, it's using something like this, right? It has a convolutional, or I should stop using that word. It has a neural network that is it takes features from the image that you uploaded, and then it compares those features to a big database of features that it's gotten from all of these images that it knows about, and then it finds you the one that is the closest, right? Using some really usually very simple distance metric. So like it'll give you more frogs, right? It'll give you more zebras. Right, so I query with a zebra and I get a whole bunch more zebras. And notice like a lot of these images have very different colors, like a lot of them have different backgrounds, but the thing is that the features of the zebra are the things that really kind of stand out, and the background ends up being not as important. So you can also use this to find paths between images. There's a really cool online application by an artist named Mario Klingemann called X Degrees of Separation, where you can take a picture like from a museum and another picture from a museum, and then find a path through other pictures from that museum where it's like kind of a shortest path. So, well, that was probably a bad explanation, but like, for example, like, okay, without museums, so let's say you get a random image of a piano and a random image of a motorcycle. So can you connect the piano to a motorcycle using other images? So it kind of goes from piano to like a small piano to a chair with wheels, to a wheelchair, to a motorcycle. So this is kind of fun. I really like also this one. So this goes from a yin yang to a panda bear through a soccer ball. Yeah, so this is actually, I think, perfect. And also you can use this for data visualization. So you can organize images according to, you can organize images automatically so that similar images appear next to each other. So this is a technique called t-SNE. So here you can see that like all of the monkeys are kind of near each other, and there's a section with, insects, yeah, sea creatures, and so on. This is some software that I released online, and let's see if I can find it. Yes. So this is some software I released online. Lots of people started using it to make like cool versions of this. So this is basically made by a student at Carnegie Mellon University, basically organizing IKEA, the IKEA catalog. So this is all of IKEA items. So all of the here's all the TVs. So the only question is, why isn't this IKEA's homepage, right? This should be how you browse IKEA. So back to the slides. you can use t-SNE not just for images, but you can use it for audio. You can use it for any kind of data. So this would be a cool way of organizing sound in space. I actually have a demo for this too, but it seems to be broken, as I just learned like shortly before the workshop, so I can't show it to you. But but you can find the software online on ML4A. So also with text, so this is like organizing Wikipedia articles of so-called political ideologies. And so they're organized according to like the similarity of the topics they deal with, right? So there's like, there's like a nationalism cluster here, and there's like here's the nationalism cluster. There's I don't even know. I haven't looked at this in a long time. Anarcho-capitalism, National Socialism. Anyway, impossibilism. I've never seen that. What is that? Does anyone know what that is? I learn something new every time I look at this image. You can embed, you can also do something similar, embedding language into space, so words, and not just words, but sentences and phrases and whole texts, and embed them in the space in ways that preserve their properties, and where similar words, contextually similar words, appear close to each other. And what's really cool about this is kind of what are called word vectors, is that you can also capture relationship vectors. So for example, if you look at the vector between the word vector for king and the word vector for queen, it'll be similar to the word vector between man and the word vector for woman, right? Or host and hostess, or I don't know, like whatever whatever gendered words you can find. You can also like parts of speech, walking to walked, swimming to swam, countries and capitals, right? So there's Turkey and Ankara. And then the demos. We actually made pretty good time. Not bad. What I'm going to do now is I'm going to show you a few demos that you can do, and I'll kind of go through them quickly. They're online, but you should be able to follow along. So these are a whole bunch of demos of fun and creative things that you can do with neural networks extracting features from images in real time, right? So let me show you what I'm talking about. First of all, if you want to follow along, which you're completely welcome to do. Let me see if there's anything. Oh, I'll come back to that. Okay. So if you want to follow along, please go to this URL. Like, I know it's a little weird I couldn't find a good way of sharing the link. So I'll let you kind of copy that. Yeah, take some pictures. So this URL is a link to this Google Doc that I made. Hopefully I made it properly public. Please tell me if you can't, if it doesn't load. And it just has a few links to examples that I'm going to show you. Yes. You can always check this later. This will all be online. Yeah. So does everyone have that? Is anyone copying? Okay. It's all good. Okay. Cool. So once you get to this, you should see what I see, and then please click on this ml4a.github.io/examples. And that will get you to this page. Okay, so I just got rid of the link. Everyone's okay with that? Everyone's got it? Cool. So this page has a bunch of examples here. I'm not going to go through all of them. You can go through them in your own time later. But I'm going to show you at least like one or two of them. So let's actually pick one. Let's show. Let's do the classification simple. So this is the first one. So if you click into this, it should ask. Oh, okay. Sorry, there's one. I made a mistake here. So it needs to be HTTPS because it's using the webcam, and the webcam won't work if you do HTTP. So the link is wrong. It does the HTTP version. If you change this to HTTPS, I gotta fix that. But yes, you should get this. This should work for most people's computers. If your computer is older than, let's say, 5 years old, it may struggle with this, but it tends to work for most people, especially if the internet is good, which it seems to be. Raise your hand if you see this. Yeah, not bad. Okay. So what this is we're going to train this. We're going to train a neural network to basically discriminate between 3 different kinds of objects that we put in front of it. So what I'm going to do is I'm going to take my phone, I'm going to place it in front of the camera, like so that it's visible. And then you see this button over here, I know it's a little small, it says class 0. I'm going to click on it. The first time you click on it, it might take a few seconds to do anything, but after a second you should see like there's a little number 1 that popped up next to it. That means that we recorded an image and associated that image with the class label 0. So now if I like start to click this a lot and maybe move the phone around, I'm basically recording lots and lots of examples, lots of images that show my phone in front of the camera. Right? And now, if I place like the water bottle in front of the camera, and then now I start clicking on class 1. So now I'm recording examples of class 1 and associating it with the water bottle. And now if I do the same thing, except now I'll just have myself in front of the image. So now I'm just going to start writing class 2, maybe move around a little bit. And then let's say 30 per class or so, and then I'll hit train. And what's going to happen is it'll give me this loss, and then it'll kind of stop, and then it goes done training. Now what we can do is we can go guess. So now if I click on guess, it goes, your custom model labeled this as 2, right? Because we labeled this as 2. So if I put my phone in front of it and I go guess, it goes 0, right? 2, 1, 0. So you get the idea. You can actually train these image classifiers on very, very little data. And it's very quick. It can actually tell you what's inside of the image very quickly. And this is all, let me show you actually the code for this, because how many of you have some programming experience? Okay, lots of you. Okay. How many of you have some JavaScript coding experience? Okay. So let me tell you a little bit about how this is made. So this is using 2 libraries, 2 JavaScript libraries. One is called ML5, and the other is called P5JS. Let me just describe them for you. So ml5js.org. This is the name of a library that's being developed at my university, NYU. Basically, it's a library that is making it easier to use another library called TensorFlow.js. And maybe some of you have heard of TensorFlow.js or TensorFlow. TensorFlow.js is the name of a very new library being developed by Google. It's less than 1 year old. It's a JavaScript library that basically does GPU-accelerated deep learning inside the browser. So that's really, really cool. If you had told me this 3 years ago, I wouldn't have believed you that you could do this inside of a web browser, but here we are. Now, TensorFlow.js is definitely difficult to use for non-experts, right? And ML5 is basically a machine learning library like for the rest of us. And it's basically making it really, really straightforward to create machine learning examples in the browser. And the thing that I just showed you is basically written on top of it. So and it's actually just like if you go to the classifier, the feature extractor, and let me actually just like quickly show you the code. Classification simple. Let me just go into that. So, and then the other library is using another library called P5JS. P5JS. So P5JS is a basically also a JavaScript library that is bringing you processing for the web. And this is like very opportune because Casey Rios, one of the original developers of processing, is here, and Lauren McCarthy, who is the developer of P5JS, is also here. So maybe some of you have seen their work here. P5JS is, basically makes it very, very easy to create graphics and sound and interactivity on the web. So these are the core libraries that are being used. And then inside of the code, if you look at it, how many of you have used P5.js? Okay, some of you. If you look at this, the code for that thing that I just showed you is extremely minimal. It's like really, really nice and small. Basically here, there's just an HTML page. It's just 34 lines. It downloads P5.js and ML5 from the web. And then it creates some HTML. You can already recognize it. Then it creates a button that says train and a button that says guess. And then this is the file sketch.js is a P5.js sketch that imports ML5. And then ML5 creates all of the machine learning components. And I'm not going to go through this in a ton of detail, but you can see that it's a very short program. And actually, like, it looks like it's 80 lines. But functionally, it's actually like 30 lines because, for example, this right here is just like making the buttons in HTML. So it just looks long, but it's actually really simple. But then the main thing is that it goes, okay, I'm going to create, these are the main lines of code. Create a captured, like a video capture device, right? Put it inside the div video container. Create this so-called feature extractor from ML5. And then when it's ready, go to the function model ready. And then it has this many classes. And then we create a classifier on top of it. And then in classify, basically it's already attached to the video. And so when you click classifier, classifier runs. It gives you the results, and it calls this function got_results. And then got_results is down here. And then that's it. It's like really, really minimalistic. So let me show you now an example that's the same thing, except slightly more complicated and does something functional. If you go back to this, you can see, go back to here. Let's look at the, I'm just going to go straight to the Pong example. So the Pong example is doing almost the same thing, except it's doing, again, we have to change to HTTPS. It's doing almost the same thing, except instead of controlling a button, it's controlling a slider. So this slider, we're controlling the slider, and the slider is associated with the value of this paddle. You guys know the game Pong, right? So what I'm going to do is I'm going to put my phone in front of here, and I'm going to put the slider all the way to the left. I'm going to take a whole bunch of images, associating my phone with the slider on the leftmost side, right? And then what I'm going to do is I'll put the slider all the way in the right. I'll put the water bottle here, and I'll take a whole bunch of samples. And then I'm going to click on train. Right, it's training again. And then once it's done, I can click start playing, and I'm going to play Pong against like a really, really simple AI. So now, like, this turns out to be like actually super difficult. So I already lost. Okay, here we go. Actually, I need to fix this because I can't see myself in the camera, so it's actually surprisingly difficult. I got one. All right. So far, I've never scored like on the on the computer. Oh, no, it's unbeatable. This go. Anyway, you get the idea. I need to make this game like more playable. It's really, really actually quite difficult. Let me show you a couple more examples. This will be fun. So go to PoseNet Sound, and again, you got to change to HTTPS. And turn down your volume, like just a little bit, because this might get out of control. So basically, this is PoseNet is a TensorFlow model that actually like finds your body, finds your body. And so if I turn up the sound, it's basically playing these buttons. So now turn up your volume a little bit. We're gonna make like an amazing cacophony in a second. Like, anybody playing already? So if I stop, it should stop. It's a little jittery, so usually All right. Well, so the the sound library is actually I had a reverb on this that made it sound really really cool, but the reverb is broken right now, so actually it doesn't sound that cool. So, sorry. I think it's. Oh, I don't know. Am I attached to stereo? It must be stereo. Yeah, I think it's. There we go. I hear some bleeps and bloops. Let's actually move on. So again, like I just want to let you know about this in ML5JS and P5JS, and ML5 like has a bunch more examples that of stuff that is really quite functional. So like if you go to, I'm going to show you one more. Like let's go to YOLO. YOLO stands for you only look once. This is a neural network that can detect objects. It's called that because it works really fast by only allowing the neural network to look at the image once. That's why it's called that. It's also called that because it's made by a madman, but that's another story. So now I'm going to click Start. And what it's going to do is it's going to start labeling things inside of the image, in theory. Or not? Is it broken? No. The webcam is fine. Maybe it just doesn't see anything. So, hello. Okay, well maybe it's working for you. For some reason for me, it should be coming up with boxes that say like person and phone. If it's not, then maybe the demo is broken. So this is an open source project that's being developed by just a few people. So like for anyone who's interested, who has some, who's interested in getting involved in an open source project, both ML5 and P5JS are like community run efforts. So very much open to contribution. So like for those of you who are interested in participating in the development, you can find out all about that if you go to the actual website. And let me show you one more thing. Like let's look at the style transfer with webcam. Okay, so this is doing something called style transfer, which is going to transfer the image, this painting style, onto my webcam stream. And it does so not blazingly fast. You know what? The problem is also my computer is really old, and it's running both through a projector and the slides at the same time, and so I think it's just like grinding to a halt. This will probably work for you, especially if you have a more recent computer. It's working. It's just working really slowly. It should work at like 1 frame per second roughly. And oh, okay. Yeah, never mind. Yeah, like I said, open source, open source project. So yeah, that needs to be fixed. But that's kind of how things go. Okay, fair enough. Like let's show some more things. I'm going to show you a couple more examples. Like let me show you some real-time demos. Let's just see how we're doing on time. 2:40. Got plenty of time. Good. I'm going to show you some demos. So let me show you a demo that I like to show called Ableton Osc. So anybody here a musician? Okay, we got some musicians here. Anybody use Ableton Live? Okay, so if you're not a musician, you can become one today, because Ableton Live is like so easy to make music with that even I can do it. So I'll show you. Like I'm gonna put in like a conga drum. Let's just make sure it doesn't blast the. Yeah. The guiro. I'm just picking instruments at random, except I always have the tabla because this only works with tabla. Yeah. Okay. Now what I'm going to do is I'm going to go on the master track and I'm going to find an effect. And I always like to pick a new one. So let me just find, the grain delay. I think this who knows a good. Which one is really good? Borg? Let's go with the Borg. Whoa. Wow. Okay. Okay. All right. That's perfect. So now what I'm going to do is I'm going to open up an application called Ableton Osc. And Ableton Osc is an application that's part of a collection including Covenant Viewer called ML4A OFX. So if you search for this on Google, you'll find on GitHub a repository that I'm maintaining in ML4A with collaborators called ML4A OFX. This is a whole bunch of open frameworks applications that are like basically doing a whole bunch of useful machine learning oriented stuff. And one of them is controlling Ableton Live. And so what I mean by that is, oh, actually, hold on a second. I gotta Ableton Osc. This one should work, right? Yes, okay. So now what I can do is I can click on these parameters. This actually finds all of the available sliders in this set. So I can control the tempo. And I'm going to click on the master and I'm going to go to the Borg. And I'm going to control the frequency now. Oh yeah. Well. Okay. And then there should be a dry wet, right? Yeah, let's use that. Okay, fair enough. Now what I'm going to do is I'm going to open another application, also part of ML4A OFX, called Covenant Predictor. Hang on a second. Covenant Predictor. I really need to clean up. I have like 40 of the same application all over the computer. Okay, so I'm going to add 4 sliders. And now these sliders control these. It's a little convoluted because Ableton is like not easy to control through OSC. Okay, so here's what I'm going to do. Now I'm going to do the same thing that we did before with Pong. I'm going to train this webcam to associate these sliders with some images. So like I'll put my phone in front of the camera and I'm going to record a whole bunch of samples. Yeah. Now stop recording. Let's make that really wet, yeah. Let's make the feedback really high. Okay, now I'll put the water bottle. And now I'm going to put myself in front of the camera and let's say, really make it fast. It's a little mushy, but alright, let's go with it. I've had more musical versions of this before, but that's what happens when you try to make it up. Alright, so that's me. So I'm associating my face with this sound. And then, as always, I'm going to turn this off and make it really slow. Whoa. Okay, now I'm going to just hide. So recording some samples this way. My shoulder. And now let's stop at 250. Okay, now I'm going to click train, and now it's going to train a neural network. And you know it's training because it just flashes random colors for no reason. And then when it's done flashing random colors, we can click predict. And now it's going to start doing this automatically. Yeah. Very much. Okay. Well, it's not Beethoven, but sorry. Yes, you can't. The question was about gestures. You can't do this with gestures because it just takes pictures. But in principle, you could. Yeah, there's various ways. Or you maybe face, like smiles and stuff. Yeah. For that, it would be better to use something called Face Predictor, which is another one of the applications. All right, this thing is going crazy. So let me just like. Okay. Yeah. So now, let's do another demo. And this one's going to involve you guys. Okay. So I'm going to need some help on this. We're going to play. All right. I'm going to open up an application called Audio Classifier. So we're going to train this thing to detect, to be able to detect different kinds of sounds. And you're going to make them. So basically what we're going to do is we're going to train it first on the class label 1. What I'm going to do is I'm going to set this threshold up. And I want you guys, when I do this, to all clap. Okay, so ready? On the count of 3. 1, 2, 3. Excellent. So now we're going to do that a bunch of times, and we're going to train it to recognize claps. So let me actually just, there we go. Okay, are you ready? Here we go. Good. Now I'm going to turn off threshold mode. And you know, this may not work all that well because my microphone is super messed up. But all right, let's give it a shot. What I'm going to do now is I want you all on the count of 3. This is going to be very silly, but I want you to ooh. So like a big long ooh. Okay, so ready? On the count of 3. 1, 2, 3. Like a little longer, yeah. Okay, 1, 2, 3. One more time. Count of 3. 1, 2, 3. All right, good enough. Oh, I messed it up. Actually, I forgot to change the label. All right. We'll be really quick. Okay, let's do this again. On the count of 1, 2, 3. We'll do ooh. 1, 2, 3. 1, 2, 3. I'm getting almost no signal, so this might not actually work that well. Sorry? No, it won't work, yeah. All right, one more time. Now, ah. So 1, 2, 3. 1, 2, 3. Okay, good. And now I'm going to record silence. And let's go back and do the clapping thing really quick. Okay, so threshold mode. So ready on the count of, so as I do this, start clapping. All right, that should work. Okay, so here's what we're going to do. I'm going to train this. And now, like, just give it a clap. You see it went predicted 1, so it can detect your claps. And secondly, you can do that with volume, so it's like I'm kind of cheating, but we'll show you the real thing later. So here's what we're going to do. I'm going to open up an application called Keyboard OSC, which is going to allow, which is very dangerously, allow you to control my keyboard. So here's what it's going to do. I'm going to open the settings here, and basically we'll associate the number 1, the classifier 1 with my spacebar. 2 is going to be left, 3 is going to be right, and then 4, which will be nothing, it'll just be pass. So that should work. So now, when I click Allow Keyboard Simulation, when you clap, it'll click my spacebar, basically. So what we're going to do is we're gonna play a game. You guys know this game? So here's the rules of the game. You have to make the dinosaur jump over the trees. So are you ready? Here we go. I think. Wait. You got 1 on the first try. That's pretty good, actually. All right, here we go. That's unbelievable. I've never had a class go that far on the first attempt. Like, this is excellent. Okay, all right. Well, let's before things get out of control, let me. Okay, yeah, it's okay. All right, we're gonna do something another game. Let's see if I can find it. Okay. Yeah. Oops. You guys know this game? I think it's this. Oh yes. Oh no, Flash. Okay. Wait, hold on. I found this the other day, like this. This one, I think. Wait. This was working. Super Mario Kart Online. This one. Yes, I think this works. Or it was working. These used to be a lot easier to find, but hang on a second. Okay, how about, let me see if I can. This one. What? Okay, hang on a second. Like, I'll just. No, it works. Okay. Do you guys know this game F-Zero? This is less popular than this is like one of my favorite games as a kid. It's like a futuristic racing game. So let's just play this. It's very similar to to Mario Kart. All right, here's how it doesn't work. So when you ooh, it should move to the left, and when you it should move to the right if things were trained properly. And when you're silent, it should just go forward. And so I'm gonna hit the gas, and then you're gonna drive. So let's. The directions is ooh is to the left, is to the right, and silence is straight. So don't forget to like be silent in the beginning when there's no turn. So okay, here we go. And then actually then also this I'll take off threshold mode. Okay. Let's do it. So okay. Oops. Oh no. This is disaster. Okay. All right. We'll hang on. Oh no, wait. It's going crazy because you are controlling my keyboard. So hang on. Predict. I think what we need to do is we need to make this go for longer. Yeah, 30. I think 30 should be good. Okay. And now let's do this again. Oh, here we go. Oh. You know, we were due for some bad luck after that amazing T-Rex, that amazing T-Rex experience. All right, let's cut our losses and kind of let's kind of move on. Okay, so interactive machine learning, right? That's pretty cool. So I'll show you like some examples of other things that people have done, like with this kind of idea of transfer learning. So this is a really neat thing online that someone trained a transfer learning application on things that they can hug and things that they cannot hug. So then it takes pictures of things and it's like, can I hug that? And so this ball of yarn, very huggable. This like table saw, not huggable, right? Like, so, you know, puppy, huggable, razor blades, not huggable, things like that. So other people, this is a former student of mine at NYU who made he has these glasses that can fog automatically. And so he has a camera on his head, and whenever the camera detects that he's looking at a screen, like a TV screen or a phone, the glasses fog up. And whenever he looks away from the screen, they come back on. So this is kind of a neat thing. There's another student at NYU made this neural recycle. So basically this tells you whether items can be recycled or not. And then you put a bottle in front of it and it goes, you can recycle that. You put some trash in front of it, you cannot recycle that. Bjorn Carmen here in Denmark made a little embedded device that has a camera and then a phone app that lets you train basically 2 object categories, and then it would turn applications on and off. I have a video, but I don't want to get into it. Don't have enough time. But basically, he has this cool example where, let's say you're reading a book and you have a reading lamp, and you train the thing so that when you open the book, the lamp goes on. When you close the book, the lamp goes off. So things like this, kind of like little interaction design experiences. This is an application called Doodle Classifier that I made along with my collaborator Andreas Refsgaard. I'm going to show you something by him in a second. This lets you train. This is part of the ML for AOFX collection, so you can train your own image doodle classifier. You make drawings of little drawings, and then it can detect those drawings. And so we made together. We made this thing called Doodle Toons. Let me see if I can find the original. Doodle Toons MP. Yes. So let me show you this. So basically, we trained it so that when you draw pictures of musical instruments, Ableton Live begins to play those instruments. So let me show you that. Just the bass. Yeah. That was me. So, what's that sound? Oh, that's our car crashed out. Hang on. Yeah. Just a wreck. Okay, back to the slides. This is, so Lassie here, he made like playing Tetris with his face, with a face tracker. And I got to show you what Andreas made. So Andreas did a very similar thing. Yeah, so he basically, you guys know the game Wolfenstein 3D, right? It's basically a game where you're shooting Nazis. So he's controlling, so like normally you would control this game with your keyboard, moving up, and then you hit the space bar to shoot. And he has it so that he's only controlling it with the sounds that he makes. Okay, so here we go. Well done, Andreas. Yeah. Okay, basically this is out of order. So I mentioned this whole idea of transfer learning. All of these examples are basically the same concept. You have this neural network that's trained to do image classification, and then you can learn, it's learned to discriminate a bunch of different labels, but you can actually use the representation inside here as like a feature vector that describes an image. And then you can train your own applications on top of that. So literally all of the examples that we just looked at are examples of that. Most of them are with images, a couple of them are with sound, right? So this one trick can kind of be embedded into all of these different interactive scenarios. And you can do it in JavaScript, you can do it in open frameworks, you can do it in processing, you can do it in basically every environment that, like whatever software you're using, there should be a way to do it. There's also ways to do it inside of Unity, which is really popular. Some people are using that. So yeah, that's kind of the idea of transfer learning. So yeah, all of these things are, I didn't mention also Wakinator. Wakinator is a really, so for those of you who want to create like desktop applications, but don't want to implement your own neural networks, like instead of in JavaScript, there's an application called Wakinator made by a researcher named Rebecca Febrink. And this is probably like the thing that got me started. So like when I got interested in interactive machine learning, this was already around, so like 7-8 years ago, and been continuously developed since then. So you can create all sorts of interesting interactions on your desktop. It interacts with all of these other programs, like very nicely. It kind of implements the neural network, but then it communicates with other applications over like a network protocols called OSC, for those of you who are familiar with that. And you can find these demos online. So now, okay, in the let's say 20 or so minutes that I have, I want to take you on a little tour of like deep learning, generative stuff. This is, I'll actually show you a couple things that you could do with this also. We probably won't have time to like really do them, but I'll at least show you where you can go for them later. So how many people here are familiar with Deep Dream? Some of you. So in about 3 years ago, there was the appearance of this really, really awesome technique called Deep Dream that was developed by a researcher at Google named Alex Mordvintsev, along with 2 collaborators named Chris Olah and Mike Tyka. And basically, they used this they kind of built upon this technique that had been in the research for maybe 7 or 8 years prior, which was all about visualizing what features neural networks learn. So you can kind of there are various techniques to sort of synthesize, like create new images, create the pixels, so that they activate a particular part of a neural network. So like if a neural network has the capacity to recognize an image of, let's say, a doorway, like an archway, you can use a technique to try to synthesize an image of an archway so that it activates that neuron, right? Does that make sense? That's like a little backwards. So Deep Dream is kind of taking this and putting it on sort of overdrive. The idea of Deep Dream is that you can synthesize images so that it activates the parts of a neural network that you want. And then the trick that Deep Dream does is that it basically has a neural network observe a random image, let's say, just an image of nothing, and then it finds patterns in the image, and then it changes the pixels so as to amplify those patterns. So whatever patterns the network finds, you can change the pixels to make it find those patterns even more the next time it analyzes the image. And you do this process recursively, or like iteratively, and then it just ends up developing these like incredibly weird and like very vivid psychedelic images that look like this. And then they released their software online and started and basically started doing a lot of allowing people to do experiments with it, post pictures online. I started using their software. I got really, really curious about this technique and started trying to develop it further. And I started adding I don't have time to get into the details. I'll show you a notebook in a second. But I started adding little functions to, like, let's say, visualize 2 different features at the same time and blend them using masks. So this is kind of the results of that. And what happens is there's two features that are being visualized, one on each extreme side of this image. And then in the middle, it's kind of like visualizing features that have a little bit of both. Right? There's this kind of blending thing that's happening. And you can arrange the masks in all sorts of very intricate ways. You can make them as circles. You can create video by like making a feedback loop where you generate an image and then you distort it somehow and then you run it through the deep dream process again. And then basically like you create all sorts of like really strange images. Let me show you like actually what else you can do with it. So this I submitted last year to the NIPS conference. That's like the major neural network, like deep learning conference. It's really, really major now. Like it's sold out in like 4 seconds this year. So that's not a joke. Or it's like 5 minutes or something. Anyway, you can create all these images, and this is all open source software. So if you're interested in this technique, I'll show you how you can actually get your hands on it. So distorting the canvas in interesting ways, creating all these sort of like psychedelic visuals and so on. I've had a lot of fun with this. And oh yeah, see, another thing you can do is make masks. So you're looking at the twisted, warped face of Jan LeCun, who's one of the people who really, really advanced convolutional neural networks to the state that they are today, kind of a big name in deep learning. He's also the head of AI at Facebook and the subject of this like obscene sort of warping of his face. And this is Fei Li, who started the ImageNet competition and created the ImageNet dataset that was really, really instrumental in basically creating like the first serious dataset for deep computer vision. So on. And this actually loops. But anyway, let me kind of show you some more stuff. Then there's this technique called style transfer. Let me quickly show you just, let's see, 3:10. You have a lot of time, actually. I'm making great time. I'm actually quite happy about that. It's usually quite the opposite. Let me really quickly show you, if you're interested in the deep dream process, if you go back to the workshop document, there's a link here. I don't think everyone should go to it right now because well, you can try. I don't know. You won't have time to use it right now. But there's a link here that if you go to this Colab link, well, first of all, Colab is a service offered by Google that basically allows you to execute code in your browser that uses their computers, in particular their GPUs. And this is a notebook that shows you how to do the deep dream stuff. Basically, like what you could do is if you have this, you would go to first of all, you would have to save it to your Google Drive if you have a Google account. And then once you save it, you can open it and then click connect. And then what it's doing is it's connecting you to some GPUs out somewhere probably in like the Midwest of America. And then what happens is you can run each of these code cells. So the first one downloads this model, and then it unzips it. And then I would go to this and like import a bunch of libraries, and then I would load all of this is a whole bunch of TensorFlow junk. Basically load a neural network into memory. So that takes a second. Then we can see that it has a whole bunch of layers. So if I run this, it'll tell me what all of them are called. So these are a whole bunch of layers in the network and how many neurons they have. There's lots of them. There's a network called Inception. And basically you can go through the process of reproducing these images. It gets more and more complex until you start to get like much more vivid images like this. Right? So if I'm going to go ahead and change this. I'm going to run this LapNorm multi, which does basically the whole thing with taking masks and visualizing neurons and then kind of visualizing them against the masks. And here I'm actually going to change these numbers. Like I'll do like, okay, 24 and 14. And I'll keep the layers the same. And let's make it bigger. Let's make it like 600 by 800. If I run this in the browser, it's actually going to send the code to Google. Google will do the computation and return the result back to you. And so you can create all those images that I was showing you. You can create them literally right inside of your browser using someone else's computer for free, which is kind of really nice. Of course, if you want to make a video, it's going to take a long time because each frame takes a while. But yeah, you can make stuff like this. Oh, I forgot to make this go all the way to the end. But basically, you see the idea here. Let me make a more interesting example. Okay, so you can make twisted kitties. Let's run. Let's actually go to the circular mask. Let's make this bigger. I want to make like 1,000 by 1,000. And I'll change this to be 13 and then 33, 4. Okay. So let's run this. This is going to make a circular mask and then combine two of these features where one is inside the circle and one is sort of outside the circle. And, oh, I screwed it up. So this makes errors too. I don't know what it, I can't tell what it is. What did I do? Who knows TensorFlow? I can't actually scroll to the bottom of the error. I don't know why. Invalid. Okay. Oops. So there's only that many channels. Now it'll work. Okay. So I tried to pick a neuron that didn't exist. So that's what happened. So now it's going to compute, and this will take actually a little while because I made it a lot bigger. The bigger you want the images to be, the more neurons you want it to have, the longer each one is going to take. In the near future, I'll be putting out like an expanded code base of this that has some of those techniques you saw in that really long video that I showed you. It shows how to like create masks out of images, how to distort the canvas, how to rotate it, and do all this other stuff. The notebook itself is relatively simple. It has like some simple features, but you can actually make like some pretty cool looking images. I made it really big, so this is actually going to take a little while. It'll be done in like about 2 minutes. So in the meantime, I'll go down and tell you the rest of the notebook, and then we'll come up and see when it's done. The rest of the notebook shows you how to create video. So video is all about you make one image, and then you distort it slightly, and then you make it the input to the next round of the algorithm. Because the algorithm always needs an input image to kind of go on top of. Right, so that's the basic idea. So then this shows what happens when you sort of zoom in iteratively, and you can see that like each frame is zooming in more and more, and so you can create these like, I think I have like a zoom. Well, maybe what was it? Oh, frames, something like this. See if I can. No, that's something else. In deep dream. No, not that. Video feedback. Yeah, there we go. So you can make stuff like this. This is really old, actually. Infinite zoom of deep dream junk. This technique was come up with by Mike Tyka, who was one of the like 3 principal authors on the deep dream technique, and I've been riffing on it like continuously ever since then. Okay, so I think the thing above should be done, and there it is. Okay, it's not the coolest thing, but it's kind of neat. So you get the basic idea. There's a lot of like exploratory stuff that you could do here. Lots of aesthetics that remain to be kind of seen. Let me get back to the slides. Style transfer is generating one image in the style of another. So this originally used a very similar technique to Deep Dream. Now it can be done in other ways that I'll show you in a couple of slides. But okay, making the Mona Lisa in the style of a Picasso painting, right? This kind of thing. I don't have enough time for this, but basically like it works by trying to match the features in a certain way to like match the style of the style image and the output image, and then anyway, there's a paper on it which you can read if you'd like to know more about the technique. Style transfer is actually like very closely related to the idea of texture synthesis. So you can use Deep Dream is almost kind of a version of texture synthesis, and it's very similar. Like this sort of like iterative changing the pixels slightly until it has the features you want. So like you can take an image of Google Maps and then generate a new image that looks like it, right? So this is like hallucinated Google Maps. And I developed this like feedback technique that actually loops. So if you, I forgot to make it loop. Let me quickly make that loop. And so if you look at this for long enough, you may realize that it's actually just like an infinite loop. So this is another technique that I figured out a little while ago that I'm going to put online. I've been saying that for a while, but it's turned out to be more complicated than I imagined. But this will be online like very shortly. And similar, this is some work by another artist that's doing a lot of work with texture synthesis named Sofia Crespo, and is like really making like wild, really wild images that you can see online. More style transfer stuff. And then I want to tell you quickly about generative models in these last like 5-10 minutes that we have. So generative models are representational models of data sets that are learned by a neural network. So the idea is that you, let's say, have several thousand images of faces, and you send all of those images to a neural network, and then you train the neural network to take random bits of, like random numbers, essentially, as input, and then output images of faces that look like they came from the original data set. And now you may be thinking, like, why would scientists care about this? Turns out that it's really, really useful to have generative models because it allows us to understand the underlying process that created the data, right? So there's this old quote by Richard Feynman, the physicist: "What I cannot create, I do not understand." And so the idea is, if you can model the process of creation, you can understand. Well, you can understand it. Now, for obvious reasons, this turns out to be like really, really interesting to artists. And so there's been a lot of interesting work combining these with like art techniques to make interesting aesthetics. There's kind of two categories of this. I don't have enough time to get into the details, but like there's the two most prominent versions of these are called autoencoders and what are called generative adversarial networks. And generative adversarial networks, for those of you who have heard of them, this is a technique that's been around since really, really ancient times, all the way back to 2014, when like one person got drunk, basically, and came up with this really wild idea that no one had ever thought of, which is to have two neural networks kind of locked in a sort of adversarial process where one neural network is trying to generate images, and the other neural network is trying to tell if those images are real or fake. And it turns out that this is a way of training generative models in a really, really, really good way. And so since then, there's been this explosion of research into these generative adversarial networks, GANs as we call them sometimes, that produce all sorts of really wild images, that have all sorts of interesting features. Remember I talked about that whole like man is to woman as king is to queen type thing? Turns out you can do that in image space as well, and you can subtract and add features to each other. So man with glasses minus man plus woman equals woman with glasses, and this kind of stuff. More recently, like the original GANs were just they were just like 32 pixels big. Now they're as big as they're basically almost HD. So this is some work by NVIDIA about 6 months ago, synthesizing faces. This was trained on a data set of celebrity faces. So these are just like imaginary celebrities. NVIDIA put out a 1 hour long video on YouTube of this, basically, just imaginary celebrities being synthesized. It's really, really wild, and it's really detailed, right? You can see like the individual follicles of hair. You can see like the glint in people's eyes, like eyebrows. It's really, really wild, right? And they now I don't want to get your hopes up too much. This software is open source. It turns out that this software currently, as it stands now, requires an insane amount of computation to run, like a lot of GPUs. I did manage to run one so far myself. I downloaded, first of all, before that, they released a whole bunch of models online. So making generative models of cats and bedrooms and bicycles and TV screens and cars. They actually released so when you train a neural network, you have a model. Once you have the model, you can use it to generate new images, which is really cheap. Training is very expensive, takes a long time. Generating is actually very cheap. And so they put these models online. And so I actually made these videos using the models that they put online. You can actually go onto their Google Drive and download the models to your own computer. Not necessarily to your own computer, but like one with a GPU. And then they have like a little bit of starter code that shows you exactly how to make these. And so I made some of these, like these interpolations, as we call them. I did one that I kind of like. I want to show you really this. So basically, like they have this like generative model of cats, and they trained it on many, many images of cats that they found on the internet. You know, really, really rare, like images of cats on the internet. And it turns out many images of cats on the internet are like memes, right? And so I found the meme vector. And so like I basically, you see the memes in there, like all the block letters. So really, really, really wacky, like wild stuff. And it loops. So I trained one of these on, I downloaded like around 100,000 images from WikiArts. So if you go to wikiarts.org, you'll see that there's like, it's like a Wikipedia of public domain artworks. And so I downloaded a bunch of artworks and I trained one of these progressive GANs on it. And so I have this generative model of paintings. And it makes these like landscapes and portraits and abstract works and Baroque works and all of this kind of stuff. And it looks like this. So this is as we might call it, the latent space of painting. And now I just want to mention like, okay, so like this is from 3 weeks ago. So really, really getting wild, right? So these are not real images. These are completely and totally synthetic, but hyper realistic, right? So cheeseburger, dogs, butterflies, rocket ships. So we're really approaching, like the sort of realism of GANs is really, really approaching. And so you have to ask, like, what happens when we can generate realistic images of anything? Well, one thing that happens, I have to skip this a little bit. You can do these like image filtering. So let me show you an example that ties to what I was just talking about. So another category of neural networks filters images. So style transfer is kind of like an image filter. And you can make image filters that let you, for example, like turn labels into, street view scenes, right? So this is a person drawing like a landscape. You can imagine like design software, Photoshop and Illustrator, those kinds of softwares, having features like this built in the near future. I like a little while ago, I used this software called Pix2Pix, which implements this. This is about 1.5 years or 2 years ago, to make a generative model, like a face-to-face generative model of the president of the US. And so I made like a little like Donald Trump mask, right? And now when I did this, it was like very campy. It's like everyone can see that it's fake, right? But lo and behold, like about maybe 2 or 3 months ago, NVIDIA released some more research that shows that you can generate faces like, okay, this is street view scenes. You can generate faces really realistically. So these are completely fake. They're trained on real people's faces, so they're models of real people. But the faces that are being generated are totally synthetic. And they're being synthesized from these lines. So basically, the idea is that if you can extract a few minutes of a video of somebody, you can make basically like a face puppet of them, right? And anyone can do this of anyone else for any time, right? So you can imitate your friend across the street, or you can imitate the president or the head of state of who knows where. Maybe they might not appreciate it very much. So you have to think about like what happens in a few years. When anyone can do this, generate realistic imagery of anything, and only another neural network can tell apart if it's fake or not. So this kind of stuff is like very much like in the headlights, I guess you could say. And we have to think about that, I suppose. Other models, I'm running out of time, so I'll just kind of go through these quickly. But you can have neural networks tell you like caption images, tell you this is a plate of fruit and a fork and a person sitting at a table and so on. And I mentioned reinforcement learning. This is making things play games. So you might have seen a few, this is like 2 years ago, when the company DeepMind was able to beat the world's top-ranked Go player. So Go is this game that's very popular, mostly in East Asia. That's kind of like chess, except like way more complicated. And now it has fallen to the machines, as we say. and they recently made it so that it doesn't even require training data. So basically, this program called AlphaZero learns how to play chess. And the way that it learns how to play chess is not by studying games of chess by humans, because that's the way that you would do it in the past. You would download 1 million chess games, and then a neural network or some algorithm would learn how to play chess by analyzing all those games. They don't do that at all anymore. Now what they do is they just make 2 copies of an AI that can play chess, and it doesn't know how to play at all. It just makes random moves. It plays terribly. And then they make 2 copies of it, and they make them play against each other. And the more they win, the more the strategies are weighted up. The winning strategies are weighted up, and the losing strategies are weighted down. And they do this for on 100 computers for 2 weeks. And then when it's done, I might have gotten the numbers wrong, but when it's done, it's the world's best chess player. So no humans involved in the loop. And now they're trying to do the same thing on really complicated video games. Yeah, I bet some of you are into this. And so now first of all, it's like you think, okay, video games, it's just going to be really good at video games. But remember, video games are like a simulation of the real world. And so whatever things that we have, computational agents interacting with the world, they might become increasingly good at doing things, that we can teach them how to do. So yeah, that's all. Thanks for coming out, and please get involved and stay in touch and everything. Yeah. And if you're interested, mlfrey.github.io. This is like a place where you can find all this stuff. And also it's on Twitter. mlfrey is on Twitter. I'm on Twitter. I'm also on Instagram. You guys really like Instagram here. I have like a bunch of stories. And my website is genekogan.com. Please do stay in touch. Feel free to get in touch if you're interested in any of this stuff. And good luck. Bye-bye.